So what's a complete fuel system? Well, it's exactly what we say it is. It's a complete fuel system, meaning it comes with everything. Everything you need to pull the parts out of the box and install it in your garage with basic hand tools. So injectors, rail, regulator, Teflon lined hoses built to fit the vehicle, all the necessary adapters, both electrical adapters and plumbing adapters, piece of cake, pull it out of the box, put it in, be done with it. So let me go through these in order quickly. Injectors. All the kits come with injector dynamics injectors. And for those of you who don't know, Yawpower is the engineering team behind injector dynamics. So all the injectors are built in partnership with Bosch Motorsport, and they're absolutely the best thing you can get in the aftermarket. I won't go into too much detail about that because that would just brag and probably make myself look bad. Fuel rail. These are machined in-house. They are machined from aircraft grade 6061 T6 aluminum. And to be clear, that's just a bunch of horse shit. It really doesn't matter. It's aluminum. It's 61. It's T6. It's not aircraft grade any more than a Goodyear tire is aircraft grade because they use Goodyear tires on airplanes. So let's get that out of the way right off the bat. They are machined in-house here at our facility in Arizona, and they are anodized, which is critical when you're using them with alcohol-based fuels because alcohol, both ethanol and methanol, will absorb water from the atmosphere, and when it does so, it becomes corrosive and it will corrode aluminum fuel rails. So they are anodized and they're machined here in-house in our facility in Arizona. The regulator. Now, this is somewhat unique. If you can follow my mouse here, wandering around in the upper right-hand corner, you'll see we have this machined and again anodized aluminum housing, but this holds a Bosch fuel pressure regulator. Now, the reason we use that, and by the way, it's a fixed pressure regulator, it's non-adjustable. And the reason we use that is that, first of all, the OE quality is much better typically than your aftermarket pieces. Less temperature sensitivity, faster response time. And the other thing is, being a fixed pressure regulator, we don't have to concern ourselves with you having the correct pressure. So we could send a regulator out with a gauge, but the automotive gauges tend to be, let's just say, less than accurate. I mean, we recently had one that at 3 bar, which is 43.5 psi, was off by 9 psi right out of the box. So if you put that in your car and your fuel pressure is low by 9 psi, you're going to call us back. You're going to yell at us and say, well, my system's, my car's running lean. It doesn't have enough fuel. Well, the reason is that the regulator, or actually the gauge, was the problem and the pressure was set too low. So that's why we use the regulator that we do. It's available in 3 bar, 4 bar, and I think 4.5 bar, but I don't know that we include any of those in our kits. The next thing is the hoses. All of the hoses are built specifically for the vehicle. We have one of everything here. It's designed to fit exactly. They're a crimped end hose, Teflon line, so none of the fuels that you might put through there will degrade them. And that's critical because as the engineering team at Injector Dynamics, we get a lot of pieces back that are clogged up, full of dirt. Sometimes it's due to poor filtration, but more often than not, it's because the fuel lines have degraded and we find little particles of fuel lines stuck in the injectors. That's a very typical thing. We deal with this almost daily in our service program. And so these are Teflon lined. Again, they're resistant to everything. Every single line is pressure tested before it leaves the facility. Last thing on the list, all necessary adapters. That means electrical adapters, plumbing adapters. To give you an example, if you look here at the top left image, you can see lots of little pieces there that come with the kit. On a return style system, you have to return the fuel from the regulator back to the stock fuel tank. You have to drill through the basket. We have various adapters and fittings that allow you to do that and have a proper leak-free connection there. So literally everything that you need. All right, so the next question is why? Why do I need to invest in a fuel system? Well, hopefully this picture here says it all. The simple answer is that you don't want to be the guy that's posting this picture to the forums asking what happened to your car. So on occasion, it's a bad tune. It happens. But more often than not, it's a fuel system that can't keep up. And you have to understand that all the power that comes out of your engine comes from the energy in the fuel. And that fuel has to be mixed in proper proportion to the amount of air that's coming into the engine. There's a mixture that my chemist friend might describe as the stoichiometric correct mixture, and that's the mixture that results in complete combustion. But we run slightly richer than that to keep the temperatures down to stave off detonation so we don't end up with pistons that look like this. And we have to have enough fuel to maintain that slightly rich mixture, about 20% rich of stoichiometry. Otherwise, we're gonna tear a lot of shit up. And if you don't have enough fuel and the engine runs lean, which is what happens when you don't have that excess fuel, temperatures go up and things blow up. So hopefully that answered that question. All right, I'm going to slow it down a bit as I go through some of the details here and explain the calculations involved in determining what makes an appropriate fuel system for your car. So, in terms of system design, the very first thing we have to know is what's the engine airflow. Now, as it turns out, this is a pretty simple thing to calculate. We only need to know the displacement, the RPM, the boost, and then we have an estimate of volumetric efficiency at the horsepower peak, which would be somewhere between 90 and 95%. And then we include a factor of safety. So, first step, determine how much air is flowing through the engine, because as I described, we have to have an appropriate amount of fuel, an appropriate ratio of air to fuel. Okay, so I mentioned earlier that the fuel has to flow in proportion to the air. We need a very specific ratio. Now, that ratio is dependent on the fuel that you're running. And I mentioned before stoichiometry or stoichiometric air-fuel ratio, which is the ratio that gives complete combustion of all the components involved, oxygen and hydrogen and carbon molecules, maybe more than you needed to know. But what's important is that it's different for every fuel. So if we want to maintain that excess fuel ratio of about 20% rich of stoichiometry, we have to we have to consider the fuel. In the case of isooctane, it's about 12.5 to 1, ethanol about 7.5 to 1, methanol about 5.4 to 1. So now we've got the airflow. Now we know what ratio we need in terms of air to fuel, and so we have the total fuel flow. That's the single number that we need to get this done. From here, we simply choose the appropriate parts, the fuel injectors, the fuel pump, based on fuel pressure, and a number of other things that I'll detail here next. All right, so it's been pretty simple at this point. We've talked about airflow and fuel flow and determining that one single number that we need to decide, what system to put together for you. Now we have to pick the individual components, and this is not quite as easy as it seems. It requires a lot of testing, and I'm not going to have to get very far through this before you realize that this is a job for a fuel system expert, not for some jerk off on the internet. So let's dig in here. Looking at the graph below, on the x-axis, if you can follow my mouse, voltage is across the bottom there. The y-axis is flow in liters per hour. And then let's see, what do we got here? A turbo R pump. The red line is 3-bar pressure. The orange line is 4-bar pressure, and the yellow line is 5-bar pressure. So the thing that should stand out pretty quickly is that as pressure goes up, the flow goes down. And I think everybody gets that when it comes to pumps. But the thing that might not be as clear is that it's also very dependent on voltage. So if you look at the far left-hand side of the graph at 11 volts, you can see that the flow is down considerably compared to the flow at 15 volts. So the voltage varies a great deal with all of these vehicles, depending on whether or not they have like a motorcycle-style generator like the KRX, the YXE, those vehicles, or an actual belt-driven alternator like the Pro R. So the Pro R, when it's running, is going to be sitting at, maybe 14 volts, maybe a little bit above that. Of course, when it's shut off, we don't need fuel flow when it's shut off, but it's at 12 volts because it's a 12-volt system. If you have enough load on the system, the voltage can drop considerably. So let's just say that your car is running on the dyno and you had 14 volts to power the pump. That's great. You may have enough fuel flow. You may have just enough fuel flow and everything's working just fine. And then you get out to the dunes and you've got your subwoofer cranked up and you've got your big Baja Designs lights on there, and the voltage drops from, say, 14 to 12. Well, when it was on the dyno, it had 14 volts and everything was fine. Now you get down to 12, you lose some pump flow, mixture leans out a little bit because the pressure dropped off, and that's when you can get into trouble. Now, it is not as big of a problem on the Pro R because of the alternator, or maybe you've taken it a little bit further. Maybe you're using a LaRue alternator kit, which bumps up the current output quite a bit. But let's take something like a YXC. This one is particularly problematic because it's capable of making so much power and it has such an awful electrical system. It doesn't take much load at all to drop the voltage on a system like that. So something as simple as the cooling fan kicking on can drop the system voltage by a volt. So maybe you were running at 13 volts, the cooling fan kicks on, it drops down to 12. And as you can see here in the graph, again, following my mouse pointer, the flow can drop off quite a bit. And so that's one of the ways people get themselves into trouble. They tune on the dyno, A number of things are happening there. One is that dyno tunes are typically done with a fairly cold engine. It gives really good numbers. You know, if you test it at 220 degrees water temp, it's going to make less power than it did at, say, 175. I see a lot of that. And so you've got a situation where the cooling fans aren't on, so they're not drawing any current. The voltage is high. The mixture's just fine because you have enough flow from the pump, maybe just enough. And then a cooling fan kicks on. That's enough to drop the voltage. So it's critical to realize that what you see on the dyno, depending on how the dyno tests were performed, is not the same thing that you see at the dunes or on the trails. So that's a critical thing to keep in mind. Now, the other thing that I've got on here is the flow versus voltage and pressure for the pump in our FDM, and I'll probably detail that later. But our FDM is a 1 liter surge tank. It has a Bosch brushless pump, not some Krapistani pump that has somebody's name laser etched on it. It's a real deal pump. It's brushless, so it doesn't draw much current. Wait a minute. Jeez, I've got it right here. This is really silly. Okay, so sorry about that. Maybe I should have scripted this. Here's the pump. It has a replaceable filter. It's built in. You pop those 3 bolts off, replace the filter element, piece of cake. I was going to tell you that it had a brushless controller built in here in the bottom. It doesn't because this was just a display piece, but serves a number of functions. And again, I'll go into that later, but the point I want to make is at this point is about the pump itself. So if you look here on the chart, back to following my mouse, you can see that the speed of the, or I'm sorry, I shouldn't say the speed of the pump. Well, yeah, actually I will. I'll go into a little bit of detail about that. The pump that I show here for the TurboWar is a centrifugal pump, and so the output tends to vary a great deal based on pump speed, and that's why you see the big changes here in flow. Now, the FDM has a built-in brushless controller, which, by the way, we make, along with just about everything else that comes out of this company. And rather than just supplying voltage to the pump, it's a speed controller. It senses the speed of the pump and attempts to maintain a constant speed. So what you see is that from 12 volts on up, at 3 bar, 4 bar, 5 bar, and even 6 bar and 7 bar, which is just over 100 psi, the flow is quite high. I mean, 225 liters per hour. That's good for an easy 400 horsepower, and that's at 7 bar. That's at 100 psi. And as long as the system voltage is at 12 volts or above, the flow doesn't drop off at all. And it's worth making another point that because it's a 12-volt system with a 12-volt battery, if your voltage drops below 12 volts, it's just going to get worse. What's happening at that point is that the generator or the alternator cannot keep up, and it's simply draining the battery, and the situation is just going to get out of hand quickly. So that's the key point I wanted to make. One, that with the FDM we don't have those problems that we do with the typical pump. It's also worth pointing out that the TurboWar and the Can-Am X3, at least for stock pumps, are better than the rest. If I were to show you some of these values for a KRX or a Yamaha YXZ, you would wonder how they even run it all. They're really right on the edge for even the most basic application. So we've defined pump flow. I'm trying to think of what I might have forgotten. I don't think I forgot anything. Basically, it's dependent on pressure and voltage. If you use our FDM, it's obviously far less sensitive to that. So we'll move on to the next piece of the puzzle, which is the fuel injectors. Okay, so we talked about fuel flow requirements for the engine based on the airflow, and went through the pump configuration or the pump selection based on what it is we need to accomplish. And now we make our way to the fuel injectors, and this gets a little more complicated. And of course, being the supposed injector expert, this will be the one I screw up the most. I'll misspeak, say things backwards, maybe even speak in tongues, who knows. We'll see how this goes, but I'm not going to shoot this 27 different times. I'm going to do this in one shot, so let's hope I don't screw it up too bad. Okay, so here we have a graph, again, follow my mouse, let me see, what is this? This is an ID 1750. This is a pretty big injector. On the x-axis down there on the bottom, you see the pulse width in milliseconds. On the y-axis, you see the flow rate of the injector as measured by our flow meter on the test bench. And what you see here is the rainbow-colored lines, no rainbow jokes, 16, 14, 12, 10, and 8 volts. Now, the thing I want you to look at right away is let's just look at 14 volts, the orange line. So at let me see, we have to have 1.5 milliseconds to get this thing to even fire consistently, to get it into the linear operating range where its output is predictable. So 1.5 milliseconds there, and then when we get up to the top and follow my mouse again, you'll find that at about 10 milliseconds it starts to go steeply nonlinear. So we have about half a millisecond there and about 1.5 at the bottom, which adds up to 2 milliseconds of time that injector is just not flowing any fuel at all. So if someone says, I've got an injector, it's 80 pounds per hour, and you do some math quickly and you say, okay, that's good, that flows what I need, you have to keep in mind that that's not actually what it's going to flow dynamically, which, by the way, is where the name injector dynamics came from. When we entered the market, we started showing this type of information and explaining how it affected it on a running vehicle. So you can say, well, at that voltage, 2 milliseconds, okay, that's fine. Maybe that's 80% duty cycle, 90% duty cycle, whatever the case may be. But what you have to consider is that 2 milliseconds means a lot more at 12,000 RPM than it does at 8,000 RPM. So we have to consider that. And when we do the calculations for like a Yamaha YXZ, we consider the horsepower peak to be at 12,000 RPM. Now, that's rather extreme, but I did mention a factor of safety. On a Pro R, we consider 9,000 RPM. And so, again, the amount of injector flow that we're going to lose just based on the injector dead time and the upper nonlinear range is much greater on a YXZ than it is on a Pro R or any of the other vehicles that may max out at about 9,000 RPM. And then, of course, this is just a 3 bar. As the pressure goes up, the injector flows more, and this offset changes as well. I mentioned that at 14 volts, we have to have about 1.5 milliseconds before we get the injector into its happy range. When we get to higher pressure, that changes. It may take 2 milliseconds, and again, that's going to be a greater loss of total fuel flow on a YXC than it would be on something like Kawasaki KRX. So we have to take that into account. And essentially, we have to crunch all of these numbers for any given application to make sure that not only is the pump flowing what it should at 12 volts, because we consider the worst case scenario, 12 volts. We do the same thing with the injector. We consider injector flow at 12 volts, take into account the nonlinearities that cause a loss in fuel flow, and work backwards from there. Now, the tuning tool that we have to do that is fuel pressure. So we've got 4 different sized injectors. We've got the 1050, the 1300, the 1750, and the 2600. And then we also have fuel pressure we can vary. If the 1050 was just a little bit too small, we could run a 4-bar regulator instead of a 3-bar regulator and pick up maybe 14% more flow. So these are the knobs we can turn to get the job done. So I mentioned fuel pressure, and that brings me to the next critically important part of this. And in fact, there's another video I may direct you to give you some more details. But when we talk about fuel pressure across the injector, we mean differential pressure. We mean what is the difference between the pressure at the inlet of the injector and the outlet of the injector. So let's just say that we had 3-bar pressure on the inlet, and that was a fixed value. It didn't change. And it's firing into a naturally aspirated engine at full throttle, where the manifold pressure is 1 bar. I'm sorry, measuring in terms of gauge pressure, it's 0, right? No boost, no vacuum. I sometimes get confused when I'm doing these because we talk about absolute pressure, gauge pressure, differential pressure. Anyway, so we've got 3-bar differential pressure across the injector. Now, if we were to add a bar of boost, 15 pounds of boost, what's going to happen is now we've got 3-bar pressure at the injector inlet and 1 bar at the outlet. So the differential pressure across the injector is only 2 bar, and the flow goes down considerably. So we have to account for that in the fuel system by deciding whether or not to have a map referenced fuel system or a non-map referenced fuel system. Now here's what that means. You'll notice that the regulator picture that I posted before had a little fitting coming out of the end of it, and that's what we call sometimes the boost line. We'll run a line from that to the intake manifold, and what that does is adjust the pressure based on manifold pressure so that the differential pressure across the injector remains constant. So in the scenario I just described, if we build 1 bar of boost or 15 psi, the regulator pressure will go up by that same amount. So we maintain a constant differential pressure. And so as you're going through our systems, looking at them, trying to make sense out of the numbers, you have to keep that in mind. If we look at, let's just say a Pro R from the factory, has a fuel pressure regulator that's referenced to the atmosphere. So as you build boost, the differential pressure across the injector goes down, right? So things get really ugly really quick. So these guys are getting away with this on pump gas at like a half a bar pressure, barely getting away with it. But of course, I showed you the picture of the roasted piston before, and you've all seen that partly because of Pro R's running on stock-ish fuel systems with nothing but upsized injectors, and that's part of the problem. So one of the things that happens, or one of the things that we might step you up to fairly early when you're running boost, is a map referenced return style system where we have the regulator mounted on the rail. It returns fuel back to the tank. It references manifold pressure to maintain a constant differential pressure across the injector. Now, of course, all of this adds complexity and adds cost. For let's just say, I'm trying to think of the easiest vehicle, Can-Am X3. If you decide you want to run that on ethanol, all you need to do is upgrade the injectors. Now it's still an atmosphere reference system, so the differential pressure across the injector changes. However, if the injectors are big enough, the pump is big enough to get that done. So that one's fairly simple. But on many of these vehicles, it gets more complex, and we quickly have to step up to a map reference system. Now you got to buy a fuel rail, a regulator, all the fuel lines, which are pricey because they're Teflon lined, and you can't go very far typically before you then run out of pump. Because now what happens is we've got it regulated to 3 bar, so now the pump flows more, which is a good thing. But you had a bar of boost. Now the pressure across the pump is 4 bar, and as you know from the previous slide, the volume goes down. 2 bar boost, now it goes down another bar, and the flow keeps dropping off and off and off. So I guess my point with all of this is not so much to make you necessarily understand all the details required to make these calculations, just to let you know that it is fairly complex. It's not something you can do just by asking your buddy or saying, well, I think this pump is big enough. I think these injectors are big enough. You don't have to guess. You don't have to poke it with a stick or throw it against the wall and see if it sticks. We can perform all of these calculations because of course we have flow data for all of our injectors. We have flow data for all of the stock pumps, flow data for our FDM. So when we get that number, that total fuel flow number that we need for your application, meaning your engine and the amount of boost that you're running, we start with that number and we can perform all the necessary calculations to know that we've got it right from the start. So you don't have to guess. I mentioned that being a complete fuel system, it's great because you get everything you need and you just bolt it in, but really that's secondary, or maybe that's just kind of a nicety. I could sell you just raw parts and you could do the plumbing and the wiring yourself. That would kind of suck, but really what's important is that the flow of the system, including a safety factor, is appropriate for your vehicle. There are a lot of things that can go wrong here in terms of pressure, voltage. We get it right because we've done all the tests, we've performed the calculations, and that's really the point of all this. Yeah, it's easy to install because you get all the parts, but the main point is that you put it in and forget about it. You forget about it because it's a quality part. But the other reason you forget about it is that your shit doesn't blow up. You're not the first guy halfway up the hill, right? We could sell you a tow rope and a cheap fuel system, if that's easier. But we would prefer to sell you a good fuel system. Get it right the first time before you do your mods, because you spend time on the internet. You've all seen the blown engines, and I don't know if it's fair to say 9 times out of 10, but I will say in most cases the problem was the fuel system. And so, by the way, to take this a step further, even after everything that I've told you, let's say that none of those concerns were valid, but your fuel pressure drops off a bit over time because the fuel filter becomes clogged, right? You don't have a factor of safety and you're in trouble. It's not a simple thing, but we've made it a simple thing. So when I say complete fuel system, maybe I should just say simple and how to not blow your shit up. Actually, that's what I should have said. I'm changing the website. It's going to say fuel system so you don't blow your shit up.